Hello to everyone. First of all, I want to thank all of you for your attention and your participation here. I will present the research entitled An Autoencoder-Based Representation for Noise Reduction in Distance Supervision of Relation Extraction. The research was developed by Juan Luis Garcia, Luis Villaseñor, and Felipe Orihuela from the INAOE, and who is speaking, Lázaro Bustio from the Ibero-American University. In this presentation, we will see the following agenda. First of all, an introduction of the problem and the research problem is presented. Following, the theoretical basis is explained in brief, and this leads to present the proposed method. The results obtained are also presented and analyzed. Following, a conclusion is given. Distance supervision automatically labels a data set as follows. If two entities participate in a relation, any sentence that contains those two entities might express that relation. In practical terms, given two entities present in a sentence, they are searched in a knowledge base. If they are related to each other, or the relation is placed. Otherwise, the not applied or NA label is used. This causes the introduction of noise in the label because not always that pair of entities appear in a sentence expressing the relations. Then, adversarial autoencoders allow us to obtain representations of instances fitted to a given distribution. This allows us to identify instances that deviate from the distribution and the cosine and to consider them as a possible noise. Relation extraction is a classification problem where, given a text and two identified entities, then a relation is assigned. Sentence embeddings is a technique where, given a word, sentence, or a paragraph, it returns a k-dimensional vector. In this work, we used the pre-trained embedding dance, transf, and laser as input to the autoencoder. Adversarial autoencoder is a type of autoencoder where a discriminator is incorporated to determine if the learned representation fits or not to a known distribution, and in this work, this distribution is learned from a randomly selected instances. So, autoencoders are models that projects the input to the output. The most known autoencoder there may be is principal component analysis. Autoencoders transform the input data X to the latent space C using a function f, which is known as encoder, and return X prime from C using a decoder function G. Then, adversarial autoencoders are particular autoencoder coupled with a generative adversarial network. They are trained to minimizing the error in the reconstruction of the input, and second, fitting the vector of the latent space C to a previously known distribution. Here is depicted the proposed method by the following graph. Based on the previous definition, in this research, it is proposed a method that eliminates instances considered as noise by using autoencoders. The method starts from a training set named xtrain, labeled by distance supervision. This set is partitioned by the relation of the instances. Then, the autoencoders are trained on each of the partitions, obtaining a vector representation of each of the instances. On this representation, possibly noisy instances are detected and eliminated. An instance is noisy if its distance to the rest of the elements exceeds the average of the distances. After this process, we obtain a dataset with less noise from which a classifier is trained. Finally, the model is evaluated with a label test partitioning using the imtorque service from Amazon. The architecture of the autoencoder used in this work are shown here. On the left figure, the traditional autoencoder is shown, while on the right figure, it is shown an adversarial autoencoder. Both of them has as input the vector of the sentence obtained with the pre-trained embeddings. The difference between the two of them is the discriminator part. The discriminator takes a set of instances as real and the representation learned by the autoencoder as false. It tries to predict real or fake, thus adjusting the autoencoder representations to the distribution of real instances. The first experiment here is conducted is focused on evaluating the representations obtained by different combination of autoencoder on and adversarial autoencoder with Dan, trans F, and laser embeddings. The box plot illustrated that the average intercluster distances between all partitions is smaller, which is more compact groups in the case of the adversarial autoencoder with the three embeddings. This is due to their operation principle of fitting to a distribution, which cause them to be mostly very close to each other. The highest value are obtained with the use of the pre-trained embedding directly. Another experiment that was performed here was the projection of the subset of instances of the nationality relation and the rest. The first is with the laser and the second is with the adversarial autoencoder and laser. In both of them, the points are scattered all over the space, while the third one used the adversarial autoencoder and laser and shows the formation of two poles. Remember that we gave instances of the nationality relation and of the rest. Here we can see the macro precision value of the dataset obtained after removing noise with the cosine and Euclidean distances. The baseline is the original dataset, and it can be observed that no dataset obtained with Euclidean distances exceed the baseline. In the case of the cosine distance, the baseline is exceeded by obtaining the representation with adversarial autoencoder, and laser using only the 77% of the training datasets. This allowed us to analyze the obtained results. Adversarial autoencoder-based function, laser inputs, obtains the best mean intracluster distance value, allowing more compact groups. This was tested by means of the ANOVA one-way test, and significant differences were found with the parameters described in these sections. After that, the result obtained with the X-train prime did not show significant differences concerning the X-train dataset because it can be taken as the initial set within an iterative process formed by two steps. The first step, the similar results were achieved using only the 77 instances in the X-train set, and the experiment demonstrates that the noise reduction method did not eliminate instances that significantly affects the classified selected concerning the macro precision results. As conclusion, the representation obtained with adversarial autoencoder-based function allowed grouping instances according to their relation in a more compact groups. This allowed reducing potentially noisy instances in the original dataset. The proposed node reduction approach obtained similar macro precision values considering fewer instances, which is very interesting result of this research. The macro precision obtained over the original dataset was improved only using 77% of the instances. The obtained result verified the importance of using the proposed data representation for noise cleaning before classifying relation in distance supervision task. It suggests the usefulness of adversarial autoencoder for obtaining representation for noise reduction without significantly lowering macro precision values. And here are the bibliography reference that we use in this investigation. Thanks for your attention.